Good morning, everyone. Let us continue our discussion on the mass spectrometry. In the last class, we discussed about laser desorption for ionization technique. In continuation of that, in today's class, we will discuss about the MALDI MS. The matrix assisted laser desorption bar ionization mass spectrometry was first introduced in the year 1988, and today it has become a widespread analytical tool for study of peptides, proteins, and most other biomolecules. In MALDI, that is matrix assisted laser desorption bar ionization, the analyte is first co-crystallized with a matrix. So I'll just give you a glimpse of the entire technique of the MALDI. So in MALDI analysis, the analyte is first co-crystallized with a large molar excess of a matrix compound. That means the matrix compound will be in excess when compared to the concentration of the analyte. So we can see the typical examples for matrix compound that is being used when we discuss about the matrices. So the analyte is first co-crystallized with a large molar excess of a matrix compound, usually an ultraviolet absorbing weak organic acid is used as a matrix, after which the laser radiation of this analyte matrix mixture results in the vaporization of the matrix, which carries the analyte within it. So you co-crystallize the analyte with excess of a matrix compound. The matrix compound is usually an UV absorbing weak organic acid. So once it is radiated with the laser, the analyte matrix mixture after exposure to the laser radiation results in vaporization of the matrix, which carries the analyte within it. Now the matrix therefore plays a key role or a significant role by strongly absorbing the laser light energy and causing indirectly the analyte to vaporize. So the role of the matrix is it helps in strong absorption of the laser light energy and causes the analyte to vaporize in an indirect way. So this matrix also serves as a proton donor and receptor, which act to ionize the analyte in both positive and negative ionization modes. So we'll discuss about what the positive ionization and what the negative ionization mode mean after we understand the MALDI. So this matrix play a strong role in absorbing the laser light energy and causing the analyte to vaporize, and they serve as a proton donor and receptor which act to ionize the analyte. The efficient and directed energy transfer during a matrix assisted laser induced desorption event provides high ion yields of the intact analyte and allows for the measurement of compounds with high accuracy and sub-picomole sensitivity. So the outcome is it provides high ion yields of the intact analyte. There is no fragmentation of the analyte. So this allows for the measurement with high accuracy and at sub-picomole sensitivity. So this ability, that is generating the information, such accurate information, can be extremely useful for protein identification and characterization, which makes the MALDI an exclusive tool, analytical tool to study the peptides, proteins and other biomolecules. As an example, a protein can often be unambiguously identified by the accurate mass analysis of its constituent peptides produced by either chemical or enzymatic treatment of the sample. So even if you have the peptides, so this MALDI gives the accurate masses of the peptides. The peptides what you have can be produced or might have been produced using a chemical or enzymatic treatment of the sample as a whole. So from this session onwards, we will discuss the basic MALDI concepts and instrumentation, and then we will focus on applications in the field of peptides and proteins, especially because the orientation is to understand the MALDI tool with reference to peptides and proteins. As you can see in the figure, there is a laser pulse, and then we have the sample and the matrix mixture, and you can see the analyte which is intact. No fragmentation is shown over there. That's the reason the MALDI is said to be a non-destructive vaporization and ionization method, which is applicable for both large biomolecules and small biomolecules. So as I said, the matrix play a key role by absorbing the laser light energy and causes the analyte to vaporize. So this is a non-destructive vaporization and ionization method applicable to both large biomolecules and small biomolecules. And how the desorption of the molecules or the large molecules by MALDI happen. Several theories have been put forward or developed to explain the process of desorption. Desorption is essentially the removal of the ions. So several theories, because we need to understand how the desorption occur. Several theories have been developed to explain the desorption of large molecules, especially by MALDI. Number 1, the thermal spike model. Number 2, the pressure pulse theory. I have tried to give you the most widely accepted theories which explain desorption of large molecules by MALDI. The thermal spike model and the pressure pulse theory. The thermal spike model proposes that the matrix molecules sublime from the surface as a result of local heating at low laser fluence, but above a certain laser intensity. As a result, a rapid rise in desorption efficiency is observed. Here, the ejection of intact molecules is attributed to poor vibrational coupling between the matrix and the analyte, which leads to a bottleneck in the energy transfer from the matrix to the internal vibrational modes of the analyte molecule. So what does this essentially mean? There is a poor vibrational coupling between the matrix and the analyte. The matrix first takes the energy, transfers the energy to the analyte, and the analyte, as a result of local heating, the rapid rise in desorption efficiency is observed. So this refers to thermal spike model. Heat spike. That means the heat is transferred to the matrix. Matrix in turn transfers the energy to the analyte. That causes internal vibration of the analyte molecule and the desorption happens. In the pressure pulse theory, this theory proposes that a pressure gradient is created normal to the surface, and desorption of large molecules might be enhanced by momentum transfer from collisions with fast moving matrix molecules. Right. In thermal spike model, it is about the transfer of energy from the matrix to the analyte. In pressure pulse theory, it is about a pressure gradient that is created normal to the surface, and desorption of large molecules is enhanced by momentum transfer from collisions with fast moving matrix molecules. It is generally thought that ionization occurs through proton transfer or cationization. But we know very well that the ionization depends on the matrix analyte combo, but it is not dependent on the number of acidic or basic groups of the analyte. So nothing to do with how many groups, that is acidic groups or the basic groups, the analyte has. It is not critically dependent on that number. Ionization basically depends critically on the matrix analyte combination and not on the number of acidic or basic groups of the analyte. If this is the case, this suggests that a more complex interaction of the analyte and the matrix happen. It is not just a simple acid-base chemistry that is responsible for the process of ionization. So whatever the compound you choose as a matrix, the matrix should form or should exhibit a complex interaction between the matrix and the analyte, because the ionization doesn't depend on the number of acidic or basic groups of the analyte. It all depends on the matrix analyte combination. The complex interaction, that is more critical in the process of ionization. Right. So essentially what we are trying to understand over here is what is the role of a matrix. That means it is, or it helps in strong absorption of the laser light energy, and it causes the analyte to vaporize. And we have two important model system to understand the process of desorption. That is thermal spike model. It's all about the local heat that is generated transfers the energy from the matrix to the analyte. And in pressure pulse theory, it is about a pressure gradient that is created, and we know that the ionization depends more on the matrix analyte combination and not on the number of acidic or basic groups of the analyte. Right. So now we will try to understand about the mass analyzers. There are three types of mass analyzers which are typically used with the MALDI ionization source. So till now we have understood about the ionization, various modes of ionization, and which mode is best suited to study the proteins and peptides. So in that case we are trying to understand the working principle of the MALDI-MS. So we saw how the desorption occur and what is most critical with relevant to the process of ionization in MALDI-MS. Now we will try to understand about mass analyzers. There are three types of mass analyzers which are used with the MALDI ionization source. Number one, linear time of flight. The time of flight is abbreviated as TOF. Number two, a TOF reflectron, that is time of flight reflectron, and FT mass analyzer or Fourier transform mass analyzer. So we have linear TOF, TOF reflectron, and FT mass analyzer. So if you carefully look at the figure, it is about the linear TOF and the TOF reflectron. In linear TOF mass analyzer, which is supposed to be the simplest of the three mass analyzer that we have understood, the linear TOF analysis is based on accelerating or pushing a set of ions to a detector. In the process of doing this, that means accelerating the ions to the detector, the key feature is all the ions will be having the same amount of energy. Though they have the same amount of energy, the ions differ in mass. So the ions reach the detector at different time points in a straight path. Right, in figure 1 you can observe the movement of ions. It's a straight line. The arrow is indicated from the laser ionization point to the top detector point. In TOF analysis, which is based on accelerating a set of ions to a detector where all of the ions are given the same amount of energy. Because the ions have the same energy but they differ in mass, they have a different mass, the ions reach the detector at different time point. The smaller ions reach the detector first because of their greater velocity, while the larger ions take long time due to their large mass. Right? That is the reason why this analyzer is called TOF analyzer or time of flight. Time of flight of ions differ with respect to the mass of the ions. Smaller ions reach the detector first compared to the larger ions. So the time of flight for each ion is different. Now the arrival time at the detector is dependent upon number 1, mass, as I said, and it is not only about mass, number 2, charge, and number 3, the kinetic energy of the ion. So 3 important points are considered when the ion reach the detector. That is the arrival time. Each ion touches the detector point with relevance to 3 important features, which is the mass, the charge, and the kinetic energy. Now similar to that, we have the TOF reflectron. Now this TOF reflectron, it combines the TOF technology, the previous one, with an electrostatic analyzer, that is the reflectron. That means a reflectron is used as an additional component when compared to the linear time of flight mass analyzer. So what is the advantage of using a reflectron? The reflectron serves to increase the amount of time the ions need to reach the detector. Right? Suppose if 2 ions have the mass difference of just 2 daltons or 5 daltons, there is a possibility that these 2 ions with very small differences in their mass and having the same charge, there is a possibility that these 2 ions might reach the detector at the same time in case of linear TOF. But if you use a reflectron, these ions hit the reflectron, and again they are pushed towards the detector so that the ions get more time to travel before they reach the detector. In linear TOF, the time that is taken by the ions to reach the detector is less when compared to the TOF reflectron mass analyzer. Right? So the reflectron serves to increase the amount of time the ions need to reach the detector while reducing their kinetic energy distribution. This increases resolution. So that is the advantage of using TOF reflectron in comparison to the linear time of flight mass analyzer. And resolution or resolving power is very important when we study about the mass spectrometry. One innovation that has led to a dramatic effect on increasing the resolving power of the MALDI-TOF is the delayed extraction process. What is this delayed extraction? You can see in the figure there are two kinds of extraction process that is shown. The first one is about the delayed extraction. The second one is about the continuous extraction, and the outcome is given in form of a graph. We'll just try to understand what is all about that. The delayed extraction is a relatively simple means of cooling the ions. That is possibly focusing them immediately after the MALDI ionization event. That means as soon as the ionization happens, they are not immediately pushed to the analyzer. It is a means of cooling the ions immediately after the MALDI ionization happens. So what is happening in traditional MALDI instruments? The ions were accelerated out of the ionization source as soon as they were formed. However, with delayed extraction, the ions are allowed to cool. That means the time is approximately 150 nanoseconds before they are being accelerated to the mass analyzer. So there is a time gap. If you carefully observe the two figures, that is delayed extraction figure and the continuous extraction figure, you can see the laser pulse, and then you can see the extraction phase, which is delayed by about 150 nanoseconds. So what is the advantage of this, especially this cooling phase? This cooling phase or the period generates a set of ions with a much lower kinetic energy. When they have lower kinetic energy, it ultimately reduces the temporal spread of ions once they enter the TOF analyzer. Right? So this increases the resolution as well as accuracy of the mass analyzer. Is that clear? So you can just see in the graph. For delayed extraction, you can see a sharp peak. For continuous extraction, it's a bell-shaped curve. By this graph itself, we can understand how good the resolution is with relevance to the delayed extraction in comparison to the continuous extraction. It increases the resolution and accuracy. So I'll stop my discussion over here. We can continue our discussion in the next session. Thank you very much.